Welcome student. This is Professor Meenakshi Pancha. In this lecture, we will see about the interrupt structure of 8051 microcontroller. So, let's begin with interrupt structure of 8051 microcontroller. Whenever the microcontroller is executing a program and if a user wants to service to the IO devices, then an external and asynchronous input would inform the microcontroller and that it should be complete the execution of current instruction and then fetch a new routine that will service the requesting IO devices. Once the IO devices is serviced, the microcontroller resumes operation from the point wherever it had stopped. The external asynchronous input applied to the microcontroller is termed as an interrupt. The interrupt structure enabling and disabling the interrupt programming, the interrupts and interrupt priority. Each interrupt requires an interrupt handling or interrupt handler, or also called as interrupt service routine. Whenever an interrupt is invoked, the microcontroller executes an interrupt service. Each interrupt has a fixed location in the memory that holds the address of ISR. The group of memory location kept aside to hold the address of ISR is called as interrupt vector table. Whenever the interrupt is invoked, the microcontroller performs some steps. So see what are the steps one by one. First, the microcontroller executes the current instruction and save the address of the next instruction on the stack. Second step is the microcontroller save the current status of all the interrupts internally. The microcontroller jumps to a fixed location in the memory referred to as interrupt vector table. The interrupt vector table holds the address of the interrupt service routine. The fourth step is the microcontroller jumps to the address of the ISR from the interrupt vector table and jumps to it. The microcontroller executes the ISR till it reaches the last instruction of the subroutine. The fifth step is on the receiving the RETI instruction, the microcontroller returns to the main program where it was interrupted. The microcontroller fetches the address of the program counter from the stack. The microcontroller then executes the main program of that address. Step 5 is a critical role of the stack. Hence, while modifying the content of the stack in the ISR, the number of pushes and pops must be equal. 8051 microcontroller supports totally 5 interrupts is there. These interrupts are automatically generated by internal operation, but 2 internals are generated by external signal provided. Although there are total 5 interrupts, the manufacturer data sheet indicates that there are 6 interrupts. So, including the reset pin, this because after getting a high signal on the reset pin, whatever the operation performing by the microcontroller, it will stop and restart all the operations. So hence it is also considered as a one interrupt. So there are total 6 interrupts, but 5 interrupt microcontroller, there are 3 internals and 2 hardware interrupts are there. All the interrupt functions are under the program control. The programmer is able to change the controller bits in the interrupt enabling IE. the interrupt priority register called as IP and the timer control register called as a TCON. By setting and clearing the bits in each register, the program can block any or all the interrupts. Here the figure shows the 8051 interrupt structures and control systems. When the timer and counter overflows, the corresponding timer flag TF0 and TF1 is set to 1. The flag is cleared to 0 when the interrupt generated program call as timer subroutine in the memory. There are many types of interrupts. See one by one. First one is serial port interrupt. The serial port interrupt is generated because RI and TI. These bits are logically OR to provide a single interrupt to the processor. The TI bit of SCON. The TI bit of SCON register is set when data byte is transmitted and the RI bit is in the SCON register is set whenever a data byte is received. The serial port interrupt RI and TI are not cleared like a timer interrupt. When the interrupt generates the program call, so the program which deal with the serial communication, it must be reset or clear the RI and TI bits to 0. These two bits should be 0 to enable the next data communication operation. And similarly, there are two external interrupts that are generated by the external circuits called as a INT0 and INT1. The input of the pin of these interrupts set the interrupt flag IE0 and IE1 in the TCON register. These interrupts may be edge triggered or they may be level triggered. The whole bit structure of TCON and SCON register we will see in the further lectures. For time being, you should remember to generate the external interrupts. The interrupt flag IE0, IE1 of the TCON register will be used. Here, the interrupt vector address is nothing but what? Here is one of the table which provide the information of the location of different interrupt sources. The TF0 interrupt is generated by the timer 0. Then the microcontroller branches to the vector location 000 BH. The program execution will be continued from that location till a return instruction is encountered. A total 8 byte is set aside for each interrupt. For example, total of 8 points from the location 000BH to the 0012H is set aside for the timer 0 interrupt TF0. If the interrupt service routine is short or enough to fit in the memory space located into it, it is placed in the interrupt vector table. Otherwise, an LJMP instruction is placed in the vector table to point to the address of the interrupt service routine. The remaining bytes allocated to the interrupts are unused. How we are enabling and disabling the interrupts with IE register? When 8051 microcontroller is reset, all the interrupts are disabled. Even if the interrupts are activated, they will not be responded by the microcontroller upon the reset. The interrupt must be enabled and activated by the software so that the microcontroller can service the interrupts, which can be enabled or disabled by modifying the bit in the IE register. So the figure shows the IE register here. In this IE register, there are several bits. This end is called as a LSB, least significant bits, and the right side was called as the most significant bits. For enabling bit, the one for the enabling bit, each bit should be set for high. For disabling the interrupt, all these bits should be disabled for inputting 0. When EA is equal to 0, no interrupt will be allocated. If EA is 1, each interrupt source is individually enabled or disabled by setting on clearing the enable bit. Here, the bit IE.6 and IE.5, these are used for reserved purpose, not a specific operations still have mentioned for that. But yes, IE.4 serial port interrupt enable bit is there. And ET1, this is timer 1 interrupt enable bit is, and EX1 is the external interrupt 1 is enable bit, and ET0 timer 0 interrupt enable bit, and EX0 is nothing but external interrupt 0 enable bit. IE is bit addressable register. It contains a global disable bit, and EA that disables all the interrupts at once. When the power up, the priority are assigned according to the table. First, the priority are assigned to the register by the default, but programmer wish to change the priority, then the priority can be changed by the IP register. For the priority, first priority is assigned for the external interrupt INT0, which is having highest priority than other, and next one is timer interrupt, and third one is external interrupt INT1, and timer interrupt 1 TF1, and serial communication RI and TI. The last priority is having TF2. So in the interrupt priority, the TF2 is having lowest priority, and enable interrupt INTU is a highest priority in the interrupt table. If two requests of the same priority label are received at the same time, then the internal pooling sequence determines which request is serviced. If two requests of a different priority are received at the same time, then the request having the highest priority label will be serviced first. Which one is having highest priority? If that interrupt is generated, it will serve first, and next service will provide for other instruction after completing the task of first interrupt. Within each priority level, there is a second priority structure determined by the pooling sequence. The interrupt priority table modified by the programmer, a register called as IP register. IP is nothing but interrupt priority. The programmer can set the priority of the register by using an interrupt priority register. The interrupt priority register is also a 8-bit register, which is having PX02, PX0, PT0, PX1, PT1, and PS. These are the main bits which can be set the interrupt by particular operation. PS bit is set for the serial port interrupt, and PT1 is set for timer 1 interrupt. PX1 is external interrupt, the last 3 bits are reserved for the future use. When the 8051 is executing the interrupt service routine, in order to provide a service to an interrupt of another interrupt is invoked, then in such case, if the newly invoked interrupt is having a high priority, then only it can be interrupt the previously reserved low priority interrupt. It is an interrupt inside the interrupt or nested interrupts. So which is also called as a nested interrupts. A low priority interrupt can be interrupted by a high priority interrupt but not by an other low priority interrupt. The microcontroller interrupt latch and kept internally. This allows the low priority interrupt to be serviced after the high priority interrupts are being serviced. It is possible to trigger the interrupt by a software, but it can be achieved by the simple instruction that set the interrupt can cause the microcontroller of 8051 to jump the interrupt back to table. So why we cannot reset instead of RETI1? So when RET and RET1, both these instructions written to control the main program from the subroutine ISR. However, the RETI instructions clear the interrupt service flag after servicing the interrupt. These allows the 8051 microcontroller to accept a new interrupt. If we use RET as a last instruction of an ISR, then after the initial interrupt, all other interrupts will be blocked till the initial interrupt is serviced. Hence, RET1 must be last instruction of ISR. This is the interrupt structure of 8051 microcontroller. So, it's enough for the day. We will see in the next lecture timer and its mode.